Welcome to lecture 4.2 for exponential functions. One thing to note, we do not cover graphing by transformations or objectives 2, 3, and 4 in Math 103. So first question, where do exponential functions come from? Well, basically, exponential functions come from what we observe in real life. As basically most of math comes from. For example, when a species is introduced to a new environment, it often has no natural predators and multiplies quickly. Like in Hawaii, we would have maybe mongoose or rats, right? Not a lot of natural predators in Hawaii. This situation occurred in Australia in 1859 when a landowner named Thomas Austin released 24 rabbits for hunting. The rabbits reproduced so quickly that within 20 years they were referred to as a grey carpet on the continent and drove many native plants and animal species to extinction. Because a pair of rabbits can produce on average 7 surviving baby rabbits a year. They produce so quickly. Let's just take a look at a small sort of mini example with bunnies to get an idea of what exponential is talking about. So if you started out with 2 bunnies and after each month, each pair of rabbits has 2 babies, how many would you end up with after 4 months? Well, first let's go ahead and draw our bunnies. I'm just going to pretend that these are bunnies. Okay, so this is the first pair. And they have 2 babies after 4 months, right? After 1 month, sorry. All right, so let's go ahead and take a look at our chart. So if we have, this will be the month. And then we have the number of rabbits will be the other value. So at the beginning, month 0, we had 2 rabbits, right? So after the first month, how many rabbits did we have? Well, we had 4 rabbits. All right, so another month goes by, and each pair, remember, has babies. So this pair would have 2 babies. Looks like some incest going on. And then this pair would also, once again, have 2 babies. Not the best diagram, but okay. So there we go. Now, how many rabbits do we see? 2, 4, 6, 8 rabbits. Okay, that was just month 2. So now month 3. Okay, each pair is going to have children again. So let's say that this pair has, this pair has, this pair has, and this pair again still has. So they each have 2 bunnies. Rabbits don't seem to mind who their cousin or sibling is. All right. Now how many rabbits do we have? Well, let's see. 2, 4, 6, 8, 10, 12, 14, 16 rabbits. Now we got to get on to month 4. That means each pair that we have is going to have bunnies. So let's see. Starting from the top pair. This pair has a group. This pair has another batch, this pair has a batch of babies, this pair has a batch, 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 ooh, and this pair has a batch. How many bunnies do we see? One. Okay, these guys had their twins, just filling out the batch that we saw. And imagine, if you don't have any natural predators, nothing is killing these things except for old age, pretty much. All right, so now let's go ahead and count out our bunny population. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 times 2 is going to be 28 bunnies. Wow. So just at the end of 4 months, if each month they just have 2 babies, each pair, we'll end up with 28. And we only started with 2. That grows so fast. And that's kind of what exponential is. It just starts growing bigger and bigger and bigger really, really quickly. Okay. Versus just a normal linear equation that we've been looking at before. So let's take a look at graphing exponential functions using a table of values. So for definition, let b be a constant real number such that b is greater than 0 and b is not equal to 1. Then for any real number x, a function of the form f of x equals b to the x power is called a exponential function with base b. A few quick important features to note about exponential functions. All right, so the domain of an exponential function is going to be all real numbers. The range is going to be 0 to infinity. And we have the line y equals 0, which is our horizontal asymptote. And the function always passes through the point 0, 1, because remember our function is b to the x power. So anything raised to the 0 power will end up being 1. All right, so those are some few main good things to remember for exponential functions. Definitely something to keep in mind for an exam. So let's take a look at example 2. Now notice in the definition we have this strange requirement that b needs to be greater than 0 and b can't be equal to -1. Where do those requirements come from? Well, it has to do with what people are deciding must be exponential functions. So normally with an exponential function, which is going to be the one we have right here, because notice, what is our base? Our base is 2, which is greater than 0 and not equal to 1. So this is indeed an exponential, or this is, an exponential function. So let's take a look at what the graph ends up looking like and figure out what's an appropriate function. We'll go ahead and graph using a table of values. Please note we'll not use transformations in this class. So for table of values, I usually just pick values like -2, -1, 0, 1, and 2. Just to get a good basis, pick some negatives, pick some positives, and pick 0. So if we pick -2, this is 2 to the, well, x is supposed to be -2. Well, that's an exponent, so that's going to be 1 over 2 squared, which is 4. Then we'll have 2 to the -1 power, which would be 1 over 2. And then, let's see, 2 to the 0 power, which is, 1. 2 to the 1 power, which is going to be 2. And lastly, 2 to the 2 power, or second power, which will be 4. So notice, interestingly, none of our answers come out being negatives, even if we raise it to a negative number. Okay? So negative number values are only going to end up giving us fractions. Definitely an interesting point. Let's go ahead and graph this. I'll graph it in blue. So we have the point -1/2. And then we have the point -2/4. Oops, let me back that up. -2⁴ power. And then 0 to 0, so 0, 1. And then 1, 2. And lastly, 2, 4. So if you notice something about the way this graph is it starts to head upwards, and it's going to start heading upwards pretty fast. And then it'll go closer and closer to the horizontal axis, but it won't actually touch it. One thing to note, whenever you're graphing an exponential function, please include the asymptote with it. So this is basically an example of an exponential function. It heads up in a nice curved, sharp shape. Now let's take a look at the two options that are actually going to not be exponential functions, and we'll see why. Okay, so the first thing we said was we can't allow b to equal a negative value. It had to be greater than 0. So let's go ahead and use the same values we had before and see what we get. So -2, -1, 0, 1, and 2. So that means we're going to be raising -2 to the -2 power. And I'll go ahead and just fill these out. Raising them all to the appropriate power. So that'll be -1, 0, 1, and 2. All right, so go ahead, try to pause the video, see if you can find the answers to these and graph them. All right, so when we're trying to graph this is going to end up being, well, first let's get rid of the negative. So that'll be 1 over -2 to the second power, +2, because we got rid of the negative, which will then be 1/4. Okay, that looks similar to before. For this one, that'll be 1 over -2. Okay, this time it's a negative. Interesting. Oh, so a negative did end up giving us a negative in a sense. But remember, this is not an exponential function. Why? Because we have that -2 base. And then this will just give us 1. This will give us -2, and this will give us 4. So let's go ahead and graph this. Well, for -2, we get a 4th. Let me pick the color red for graphing this. And then for -1, we get, ooh, -1/2. That's weird. And then for 0, we get 1. So 0, 1. Okay, we know that happens usually. And then for 1, we get -2. Okay, that's weird. Now it's starting to go, it went up and then it started to head down. And then for 2, we have +4. So what this graph is going to end up looking something like is it starts to sort of bounce back and forth between values. It does this weird squiggling effect, which mathematicians were saying is for logarithmic equations, we're not looking for the ones that squiggle. We're looking for the ones that have a similar fashion, like this here, where it just sort of continually heads upwards. So the ones that were squiggling, which had a negative base, which is why it was causing it to squiggle, they said, you know what? We're not going to allow these to be considered exponential. B needs to be greater than 0. We don't want these squiggly ones. Now let's take a look at 1. Why would they say that B can't equal 1? Let's go ahead and use the table of values. Once again, I'll use the ones that I used normally. And then this is going to be 1 raised to all of these powers. I'll use green this time. Yeah, let's go with green. -2, -1, 0, 1, 2. What do we get? Well, that's going to be 1. That's 1. Ooh, that's also 1. That's 1. And that's 1. They all end up equaling 1. Okay. -2, 1. We'll go ahead and graph that. -1, 1. 0, 1. 1, 1. Really squishing it here. And 2, 1. In fact, everything is going to end up just equaling 1 no matter what we get. So we'll end up with the horizontal line y equals 1, which looks nothing like the logarithmic equations that we're trying to say are logarithmic. So mathematicians were like, you know what? This is not what we're looking for logarithmic. B cannot equal 1. And those are the restrictions, because those two do not end up looking like how we want logarithms to look like. So we went ahead and stuck with the restrictions. B needs to be greater than 0 and B cannot equal 1. So now let's go ahead and graph the following exponential functions using a table of values. Okay, go ahead. Try to give this a go and check back in with me in a second. All right, so for graphing this, I'm going to go ahead, draw my table of values. As usual, I just pick these ones. Why? They tend to work well most of the time, not always. And if they don't, I'll go ahead and pick another number. But these are just the good basic ones to work with. So we'll take 1/4, and we're going to raise it to all these different powers. So let me go ahead and set this up for that. And then we're raising them all to the, let's see, -1, 0, 1, 2. That is going to end up equaling, so the reciprocal of a 4th, so that'll be 4 to the second, positive second, And then this is going to equal to the reciprocal, so that'll be just 4. Then this is 1, 1/4, and 4 to the second power is 16th. And then 4 to the second power is 16. Okay, so we have our values. Let me go ahead and graph these. Let's see, -2, 16. Whoa. We don't actually have that. -2, 16. That's up somewhere over here. And then -1, 4. Okay, we can graph that one here. 0, 1. As usual, they always pass through 0, 1. 1, 1/4. And 1 or 2 and a 16th. And, you know, that's something we can't really graph. But give it your best shot. Just make sure it's not sitting on 0. And remember, for exponential, we're going to go ahead and have our horizontal asymptote, y equal to 0. Now, there are instances when this changes. That would have to do with transformations. But for the most part, a generic exponential equation will have your horizontal asymptote at y equals 0. Okay, let's go ahead and draw in our line or our curve. Ooh, that's not the best. I'm going to fix this. That'll do. Make sure you have your arrowheads. Make sure it doesn't look like it's trying to cross the horizontal asymptote. All right, so there we go. That is an example of an exponential function. Now we're going to go ahead and graph the next one. So this one is actually going to be one of the times when our horizontal asymptote is going to be shifted in another place. All right, let's go ahead and set up our table of values. Leave some space here for the work. So I'll do -2, -1, 0, 1, and 2. So we'll have 2 to the, what value are we using here? -2. And then what will we end up with? So we'll end up with 2 to the 0 minus 1, which will be 1 minus 1, which is 0. I'm going to go ahead and start writing these points out on the side here, just to be a little simpler. So we have -2, 0. Next, we'll have 2 raised to the power minus 1, and we're raising that with the -1 inputted. That will be 2 to the first power minus 1, which will be 2 minus 1, which is 1. So our next point, -1, 1. I'll go ahead and set these up and then try these out by yourself. And also try graph the equation. And see if you can figure out where the horizontal asymptote has moved for this problem. So how do I know that the horizontal asymptote has moved? Well, it has to do with the -1 up in the top. Notice this -1 here? It is not part of the normal exponent. So when we start to add or subtract items outside of the normal exponent, that will cause our horizontal asymptote to shift, as well as our y-intercept to shift. All right, so let's go ahead. I'm going to plug these values in. So we have 0, 1, and 2. Okay, go ahead, try these. Check back in with me in a second. All right, so that'll be 2 to the second minus 1, which is 4 minus 1, 3. So we have the point 0, 3. And then 2 to the third power minus 1, so that'll be 8 minus 1, which will be 7. So we have 1, 7. And lastly, that'll be 2 to the fourth minus 1, which will be 16 minus 1, which is 15. So 2, 15. Okay, I'll go ahead and graph these. All right, -2, 0. Then -1, 1. 0, 3. Okay, so notice our y-intercept has moved. And 1, 7. And lastly, 2, 15. That is way off the chart somewhere up there. It'd probably be a little higher, actually. And then, okay, I'll go ahead and graph this. So, the intercept actually here, or the asymptote, is actually just going to be that value there. Now, you don't really fully need to know the transformations for this class, mainly know how to do the example A, but I'll go ahead and let you know. So your asymptote is going to be along here. Remember to make it a dotted line. Y equals -1, which means our graph is going to go ahead and skirt really close to it, but not actually touch. And there we go. We have our exponential function. Now bear in mind, most of the ones we're going to work with in our course will have the horizontal asymptote at y equal to 0 and our y-intercept of 0, 1. Those are mainly the ones we're going to be looking at for our course. And those will be the ones that you'll be graded on in your exam. Transformation ones, we are not really looking at that, where the asymptotes change as much. Real quick, introducing a different base. So there's a number called e. And this number e is very similar to a number that we all know, which is pi. Or at least most of us has probably heard of pi at some point. Not the kind you eat, but pi, remember. And pi is approximately 3.14. It is not actually equal to 3.14. Because remember, pi is a non-repeating, non-terminating number. Basically, we never have a sequence that repeats. Never happens with pi. And the decimals never ever end. That's the strange and weird thing about the decimals. All right? And pi can't actually even be written correctly as a fraction, but an approximation for it is often used as 22/7. We can't actually grasp this number, which is what makes it an irrational number. Okay, that's a number we use often. So another number, like pi, which is also going to be non-repeating and non-terminating, is e. E is non-repeating and non-terminating, which makes e irrational. And we approximate e with 2.72. Now this number, how did we find it? Where did it come from? Well, it occurs naturally in nature as a product of growth rates. It comes oftentimes from looking at any sort of growth, like bacterial growth, the bunny one. I'm trying to think of another growth, but yeah. Oh, also interest rates. So it is an irrational number. Natural base. Or sometimes Euler's number. Now, I might be saying, who the heck is Euler? Well, Euler was a very famous mathematician. He was back, I'm not entirely certain how long ago, but he was known for making most of the, or not most, but a very large number of the different sort of functions and theorems in mathematics come from Euler. He's sort of like the Beethoven of mathematics. He was actually blind, which is really interesting because he could do a ton of math just in his head without writing it down. I could not do that. Okay, so we have a small little bit on the base number e. And once again, it's called sort of the natural base or the natural number because it occurs naturally in nature. Now you might wonder, where does pi come from? Well, pi kind of comes from when we're comparing the diameter of the circle to the circumference, which is the measuring of the entire perimeter of the circle. That lesson is for an entirely another video, but if you're ever interested in learning about that, you can always type it into Google or ask me for a video on how that is explained, because it's kind of neat. But alright, that is it for this section. Please email me if you have any questions on 4.2.